again. Now I will explain the solution of exercise 3, which is easier relative to the other exercises in homework 8. And I will give a solution by giving some practical information. Okay, here we have 4x4 matrices A, and let me denote its row as R1, R2, R3, and R4. And in the first part, I want to show that if we find a matrix when we multiply from the left, we will obtain a row changes. And these row changes gives us a symmetric matrix with these entries. So here note that this permutation of the rows is determined by this particular permutation, because here we want to put the second row in the first place, so that means second row goes to the first one. Third row will be placed in the second one, and 4 goes to 3 and 1 goes to 4. So to obtain an invertible matrix P, we can simply consider the same permutation on the identity matrix. So here we will write the second row of the identity matrix in the first row, and the third will be replaced by 2, and finally we will set the last row. And we may easily check that this P makes our matrix A symmetric. This is the P prime. There can be other solutions and they are also okay. But in this case we see that how the row changes corresponds to matrix multiplication. So here we have P prime, which is symmetric. That means we may apply corollary 4.18, right? So to apply this corollary, we work with the eigenvalues and the eigenspaces of symmetric matrix, of our symmetric matrix P prime. And its characteristic equation can be found as the multiplication of x minus 3 and the cube of x plus 1. For the eigenvalue 3, we may compute its eigenspace, and we can give a basis with the 1 vector. And the second eigenvalue has algebraic multiplicity 3, and its geometric multiplicity will be also 3. And here V1 is minus 1, 1, 0, 0 vector. V2 is minus 1, 0, 1, 0. And we can find the other basis element as minus 1, 0, 0, 1. So here just I compute the eigenspace for the corresponding eigenvalue minus 1. So first we observe that the eigenspaces, let me denote it by E1 and E2 here. E1 and E2 are orthogonal space. So these vectors are particularly also orthogonal to each other. And secondly, we will observe that this set of bases is not orthogonal. So only for this, we will apply Gram-Schmidt with respect to the standard inner product. Here I want to mention something. In your solutions general, when you perform Gram-Schmidt, you always consider the standard inner product. This is not true. Please be careful how the bilinear form is given in the question. But in this case, it's already given. We consider the standard inner product. And after this Gram-Schmidt process, correspondingly, we obtain a set of orthonormal bases. And these are the same vector in the solution key. And here, just to set the desired orthogonal matrix, we consider its transpose by also normalizing the first vector, which is a basis, which is chosen as a basis for the first eigenspace. And its normalization only contains the entries 1/2. It is simply obtained by U division by U. And we will consider in the second row the E1, E2 is a second column, sorry, E1 is a second column, E2 is a second column, and E3 is a second column. So here we can also observe that Q transpose and Q transpose Q is identity. So Q is orthogonal matrix. And we can easily verify P prime Q transpose is equal to Q transpose D. And this gives us the desired. Okay, thanks for your attention. See you in the next video. Bye-bye.